Welcome to my talk, ReStore, Neural Data Completion for Relational Databases. My name is Benjamin, and this is joint work with Carsten. Many organizations today want to make data-driven decisions, and the main tool are analytical queries and data warehouses. And there's a central assumption, namely that the data is complete, meaning that all tuples you expect to query are part of your dataset. Traditionally, that was the case because the data came from internal, well-curated sources. So, for instance, internal systems populating your customer and order tables. Today, the data is often incomplete, meaning that you have missing tuples because you use additional, useful, but incomplete information. For instance, tables from open data. But there are many more sources of incompleteness. You could have systematically missing data, for instance, really the high rents in a housing price data set, expensive data collection, as is the case for survey data, or the integration of independent databases or augmentation with open data. Let me give you an example for the last one. Here we deal with a housing price dataset in the US with a complete neighborhoods table with state and population density. And we only have apartments publicly available in some states. In others, apartments are missing. And that's why our dataset is incomplete. And now if we want to use this for analytics, this can quickly become problematic. Because there are two challenges here. So one is we might end up with bias in the incomplete data sets. So for instance, we could have more apartments from states with a really dense population and thus higher rents. So as an example here, we have an average rent of $2,500 on our incomplete data. But if we also include the 3 green tuples that we don't have in our incomplete data set, we actually get an average rent of just $2,200. So we overestimate the average rent. And now if we use this query result for decision making, there might be problems because we have inaccurate query results. So it's not really usable for decision making. And strategies today, it's largely ignored because we just assume that the data is representative. And as I've just shown, this is problematic. But also you could just complete the data manually, but this is a really expensive and error-prone process. That's why we came up with ReStore. Here I have a little example that explains how ReStore works. Again, a housing schema with schools and neighborhoods and apartments, whereas the apartments table is incomplete. And now if we want to compensate for this incompleteness, we of course have to use the complete tables because this is the only evidence we have, neighborhood and school tables. And here the idea for ReStore is to use the evidence in the complete tables to synthesize missing apartment tuples to make up for the tuples we didn't have in the original dataset. And for completions, we now consider correlations. So for instance, we know that a really high population density also causes higher rents, and we exploit this correlation to synthesize the missing tuples. A little bit more detail, we learn machine learning models for data completion using evidence from the complete tables. In particular, in the paper, we suggest autoregressive completion models. They are based on autoregressive models to synthesize the missing tuples. And we also want to capture all the evidence in the schema. And that's why we also come up with schema-structured autoregressive models. And they can capture additional correlations, things like few students cause really high rents in schools. So they can really capture all the evidence from all the complete tables in a schema and thus lead to more accurate completions. In the evaluation, we asked whether ReStore can reconstruct a complete database. And as metrics, we used the bias reduction. This is motivated by bias datasets. And this measures the debiasing of a certain attribute where 1 is best and 0% means we're just as good as using the incomplete dataset. And now we did an evaluation on real world data. On the y-axis, you can always see the bias reduction from 0 to 100%. And we varied a number of parameters, including the number of incomplete tables, bias attributes, removal rates, etc. Don't get confused by this plot, but the main takeaways here are that we can get bias reductions up to 100%, meaning that we get a perfect reconstruction. We are always better than using the incomplete dataset, which means a bias reduction of 0%. And the accuracy varies a bit. And that's why in the paper, we come up with confidence bounds for the completion. In the paper in general, we have many more details. So we can also complete data sets with multiple incomplete tables. We provide confidence bounds for the completion and show experiments with end-to-end query errors. The code and data is also available on GitHub.